So we're going to take a moment and talk about hydrates. A hydrate is a compound with water or H2O molecules attached chemically to the ionic crystalline structure. So for something to be considered a hydrate, it has to be able to have these water molecules chemically attached to the ionic crystals. So it does have to be an ionic substance in order for this to occur. So we have a few examples here. The first one we have is CuSO4. There's a dot here that you can see. That dot indicates that it is a hydrate. So how do we go about naming this? Well, this would be copper 2 sulfate, which is what we would normally have because sulfate has a -2 charge, indicating this is copper 2. And then we would use the covalent naming prefixes to indicate how many waters. So we have 5, so it would be pentahydrate. Penta meaning 5. That indicates it's that specific hydrate. Different ionic substances have different quantities of hydrates associated with them. The next one we're going in the opposite way. Again, sulfate has a -2 charge. Calcium has a +2 charge. But because calcium is an alkaline earth metal, it doesn't get Roman numerals. That's why nothing's there. So we're going to have CaSO4. The charges cancel out. And then whenever you draw it, I usually draw a significant dot or a pretty big dot to indicate that it's a hydrate with 2 H2O because it's a dihydrate. The next one we have barium chloride with 9, so it's going to be nanahydrate. The water molecules can be removed by heating the compound so there's a small typo in your notes here. This not needs to be crossed out. This is evaporation. Therefore, it is not a chemical change. This is a physical change. Because the water molecules are there, they can be removed by heating. You're not changing the chemical nature of the substance. And we're just going to leave off the last part there. So we follow the very same rules we do for percent composition here. The main difference is that we now keep the water molecules together. So we have lead to nitrate. Usually in these types of problems, you're calculating the mass of the water. So you can keep the substance kind of together. Lead to nitrate would be PbNO3, 2. So NO3 makes it nitrate. This 2 on the outside is because the lead has a +2 and the nitrate has a -2. And then it has 3 waters. So I always like to look ahead at the types of problems we have. Usually in a hydrate percent problem, they're asking you about water. So you can keep this in 2 parts. You have to keep the water together, but you can also keep the salt, or in this case the lead nitrate, the lead 2 nitrate together as well. So we're going to do the same process we did before. So we'll have the PbNO3, 2, as well as the H2O. So we're going to calculate the molar masses here. The H2O we have 3, so it's going to be 3 times 18.02. So I added 2 hydrogens plus 1 oxygen. And then the lead nitrate, I have essentially 1. So I'm just going to calculate the molar mass of the whole thing. On the periodic table, lead is a little bit different in that it only has a 1 decimal place. Most of our other elements have more. So for lead, when we calculate the molar mass, we have to be a little more careful. Because of this, only having a tenth, our molar mass is only going to be able to be calculated to the tenths place. So we're going to get a total molar mass here of 331.22 grams per mole. And then 3 times 18.02 is 54.06 grams per mole. So we want to know the percent of salt versus the percent of water, so we have to actually add these two numbers together. Oh, and I didn't write the right number of sig figs here. Let me fix that. So it should be 331.2 because of the lead. It has only a significant digit in the tenths place, so it should be 331.2. Sorry about that. So now we can add these together, and when we add them together, it is going to change sig figs. If you take a look at it, you have 331.2 plus 54.06. So you're going to have to round again to the tenths place. So you're going to end up with 385.3 grams per mole. So with that total, you're going to take the mass of the salt divided by 385.3 times 100, just like the percent problems that we've done before. And we're going to get 85.95899. Now we have 4 sig figs divided by 4 sig figs, so we need 4 sig figs in our answer. So it's going to be 85.96% salt. Oops. And then 54.06 divided by 385.3 times 100. So again, we have 4 sig figs divided by 4 sig figs, so our answer can have 4 sig figs, and we'll end up with 14.03% H2O. So again, when you add these together, it actually adds up to 99.99, but that's close enough for our purposes. So in the next example, we have a 40-gram sample of lead nitrate here, trihydrate. We want to calculate the mass of the water that is present. So what we're going to do, we're going to take the mass of our sample, which is 40 grams. Notice there's only one sig fig here. The 4 is our only significant digit. We're then going to multiply that by the percent we just calculated, 14.03 divided by 100. So of that 40 grams, 5.612 grams is water. Now, again, sig figs, we have 1 sig fig and 4 sig figs, so our answer needs to have 1 sig fig. So we're going to say 6 grams of water is present in this substance. You might be thinking, well, that seems like a lot to round up, but keep in mind, this 40 grams is a very unprecise measurement. We don't really know exactly the mass, so we have to show that impreciseness in our answer. That's why we're rounding so much. Why don't you try number 5 on your own, and pause the video, and when you come back on, I'll show you how to do it. So when you calculate it, you're going to multiply. You're going to do the same process. Again, we have 1 sig fig times 4 sig figs, so we need 1 sig fig in our answer. So we're going to have 10 grams of water here. Why don't you try the next two? We're calculating the percent ionic compound with strontium chloride hexahydrate. The formula here, strontium has a +2 charge, so it's going to be SrCl2 with our dot, hexa meaning 6, hydrate, which is just H2O. So calculate your percent ionic and water, and then calculate the mass of water in number 7. Okay, so taking a look at the problem, when you calculate your molar mass for number 6, you should end up with 266.64 grams per mole as the molar mass from the strontium chloride and the water together. You're then going to calculate the percentages. Notice I have 5 significant figures in both. That's due to having such large numbers here. I was able to keep 5 sig figs there. So then in the next problem, you're multiplying the 0.5 grams by the percent of water. So you end up with 0.203 grams of water of the 0.5 grams sample. So it's really kind of odd to think about how much water is in some of these substances, because these substances are all solids. It's not like you have liquids or gases here. They're normally in the solid phase. It's not showing up.